For the given expression y equals x squared plus 3x, we're being asked to find the first derivative, the second derivative, and the equation of the tangent at x equals 1. Before we differentiate any expression, what we need to look for is an expression that has terms in the form of ax to the power n, where a is the coefficient or the number at the front, and n is the index. So if we do have a square root or a fraction where an x term is on the denominator of the fraction, it would be wise to rewrite the expression so it is in the form of a multiplied by x to the n. Once we've got each term in the form of a multiplied by x to the n, the process to differentiate is quite simple. We take the power or the index, in this case n, out the front and multiply it by the coefficient, in this case a. So we get a multiplied by n. We then reduce the power by 1, so the index n becomes n minus 1. Let's have a look at how we do that process with the equation y equals x squared plus 3x. Now what we're about to do we don't have to do every time, but we'll rewrite our expression as 1x squared and 3x to the power 1. It's exactly the same as x squared plus 3x, but we'll do this to make the process of differentiation very clear. So we can see with the first term, we take the 2, which is the index of x squared, and multiply it by 1 at the front. We then reduce the power from 2 to 1. In the second term, 3x to the power 1 becomes 3x to the power 0. That's because the 3 is multiplied by the index 1, and we reduce the index by 1 to make it 0. Of course, we can simplify all of that, so the derivative becomes y dash is equal to 2x plus 3. And that's because x to the 1 is just x, and x to the power 0 is just 1. So let's have a look now at how we find the second derivative, which is basically just the derivative of the first derivative. So let's write out this equation for the first derivative in a very simple form. So y dash equals 2x plus 3 becomes y dash equals 2x to the 1 plus 3x to the 0. Now we differentiate it. For the first term, we use the index, which is 1, and multiply it by the coefficient, which is 2. So we end up with 2 at the front. We drop the index by 1, so it becomes 2x to the 0. The next term, we multiply the 0 by the 3, which becomes 0, and we drop the index by 1, so it becomes x to the negative 1. Now actually that x to the negative 1 is irrelevant, because anything multiplied by 0 is just 0. So the final expression for our second derivative is y double dash equals 2. So the question then becomes, if the first derivative is y dash equals 2x plus 3, and the second derivative is y double dash equals 2, what does this actually all mean? And the easiest way for us to have a look at this is to put it in the context of the graph, in this case the graph of y equals x squared plus 3x. So we can see from our original equation, y equals x squared plus 3x, that the derivative becomes y equals 2x plus 3. So what does it actually mean? Well, that helps us find the gradient anywhere on this curve. So for example, when x is negative 1, if we substitute negative 1 into our original derivative equation, we get 2 times negative 1 is negative 2, plus 3 becomes positive 1. So that tells us that when this function has an x value of negative 1, the gradient is equal to 1. And we can quickly check that. If we start at this point where x equals negative 1, the gradient there matches a movement of 1 across, 1 up. So that line matches the gradient at that point of the curve. You'll notice that it doesn't match the curve as we continue to the right, because the curve actually increases its gradient. When we get to x equals 0, if we substitute this into the derivative equation, we get 2 multiplied by 0 is 0, plus 3 is 3, so the gradient when x equals 0 is 3. It matches this straight line here. You can see again, if we go across one unit, we move up 3 places. So the gradient when x equals 0 is 3. If we look at the curve when x equals 1, we can see if we substitute into the derivative formula, 2 times 1 is 2, plus 3 is 5. So the gradient at this point is 5. So let's just list those gradients once again. When x was equal to negative 1, the gradient was 1. When x was equal to 0, the gradient was 3. And when x was equal to positive 1, the gradient was 5. So we can see that the gradient is changing by 2 units every time we move 1 unit across to the right. And coincidentally, what happens if we find the second derivative? We get the second derivative of this original equation, which is just the derivative of the first derivative, is 2. And that's basically telling us that the derivative is going up by 2 units every time we move across 1 on the x-axis. In this question, we're being asked to find the equation of the tangent to the curve at x equals 1. Now, just to describe what that is, a tangent is a straight line, and it touches the curve at the indicated point, in this case x equals 1. The gradient of the curve and the gradient of the tangent match at that point. The difference is, of course, that the tangent continues as a straight line, whereas we can see here the curve moves away from the tangent. So we need to work out this equation. So to determine the equation of the tangent at x equals 1, we need to remind ourselves that the tangent equation will be that of a straight line. So it's y equals mx plus c. So to find the gradient, the best thing to do would be to differentiate that equation, and we did that previously in this question. So we'll just remind ourselves of the derivative of this, which will be 2x plus 3. And we can substitute x equals 1 into this equation to determine the derivative. So 2 multiplied by 1 plus 3 equals 5. So because this derivative finds gradients on our curve, we know that at x equals 1, the gradient is 5, and that matches the gradient for the tangent at that particular point. So we've got m equals 5, and we can substitute that back into the equation. So we'll put here to sub into 1. So we'll call that equation 1. So that means we have y equals 5x plus c. Now we need to determine the y-intercept for this equation of the tangent. And the best way to determine the c value is to substitute a point, in other words, an x and a y value. Now to determine the point, what we need to do is go back to the original equation, because this equation gives us points, this equation of the derivative gives us gradients. So if we substitute x equals 1 here, we'll find the y value of the point where the tangent meets the curve. So we'll use the word sub, which is just short for substitute, and we'll sub x equals 1 into this equation here. We'll call this equation 2. And what we find is that y is equal to 1 squared plus 3 times 1. That's 1 plus 3, which is equal to 4. So the point 1, 4 is on the tangent. And we'll substitute this into our tangent equation, which is this one here. We'll call that equation 3. So that means we've got 4, that's the y value, is equal to 5 multiplied by 1, that's the x value, plus c. If we do that, we get 4 equals 5 plus c. We'll subtract 5 from both sides, and we get negative 1 equals c. So our y-intercept for the equation of the tangent is negative 1. So therefore, y equals 5x minus 1 is the equation for the tangent. If we go back to our original curve and tangent, and let's put the equation of y equals 5x minus 1 in and see if it makes sense. We can see here that the y-intercept for the tangent is at y equals -1. And we know the gradient was 5 because when we substituted x equals 1 into the original derivative formula, we had that the derivative was 5. Of course, we can see on the graph that when we move across 1 unit on the x-axis, we move up 5 on the y-axis. So there's the equation of our tangent, y equals 5x minus 1.